Last time we added mutation to our language in the form of data structure mutation of single element boxes. What we're going to do today is we're going to extend that so that our language has variables like traditional languages like C and Java and whatnot. So here's what I mean explicitly. In our previous language, we could write a program like the following. We could write a program like let x equal box of 3 in let f equal, actually, you know what, let me revise this a little bit. I want to do the example in a different way. We can write the program let f equal lambda b, and then what the code's going to do is it's going to say set box b to be 3, and then after that it's going to return 5, and then we can say let x equals box 0. Then we can write the code let y equals f of x, and then what we can do is we can do unbox x. Okay? And this program is going to return 3 because we're going to box 0, send it into f, that box gets changed to 3, we return 5 to y, and then we unbox and we get the 3. Okay. Actually, this is kind of a stupid example. It's not really, we're going to use an example like this in a moment, but actually, I think I really want a different example for variables, so sorry. Okay, so let's do this one. So we'll say let x equals box 0, and then we'll say set box of x equal to 3, and then we'll do unbox x. Okay, so this program should return 3. So this is what we can do inside of our J6 language. What I want to do is I want to introduce J7, and J7 is going to allow us to write the following program. It's going to allow us to write let x equal 0, and then we can just write set of x3, and then just x, and it will also return 3. Notice that we don't have to explicitly box anything. We never have to say, now is the time that I do the boxing. All right, so that's what our goal is. Let's talk about what changes we need to make to our language. So our J7 language is going to have the following expressions. It's going to allow us to write set of x, e. Now notice that this x right here is explicitly a variable. It is not a, it's not an expression position. You have to have the variable itself. In C and Java and whatnot, this is called an L value, a value that is allowed to be on the left, something that could be assigned. And here's the way that we represent that. What we do is we have a rule that says when you call a lambda, with a value, first of all, what did we used to do? What we used to do is we used to say that this is going to turn into going into the body, finding all the x's, and replacing them with b. That's what used to happen. This is the old thing in J6. Okay, but the new thing we're going to do in J7, we're going to change it so that when you have a function call, we're going to allocate a new pointer. And that new pointer is going to point to the value. And then we're going to go inside the body and find all the uses of the variable and change them to unboxing of that pointer. Okay? Then what we're going to do is we're going to make it so that when you call set on unbox of some pointer and a v, then what we do is we update the sigma to point to the new value, and we return that new value on. Okay, so this is a little trick where every time you call a function, you also allocate memory for it. And this is basically the way that normal programming languages work. When I say normal, I mean like C and whatnot. Every time you create a variable, it also allocates space for that variable, and allocating that space allows you to modify it. Okay, now, it's of course possible to implement something like this inside of your CEK machine as well. You would make it so that in the rule for applying a function, you would allocate space, and when you got to a variable, you would look up that variable name in the environment and it would point to a pointer. The idea is that in the CESK machine 0, your states were an expression, an environment that mapped variables to values, a store that mapped pointers to variables, and then a continuation. What this would do is you would have a CESK machine 1, and its state would be an expression, an environment that would map variables to pointers, a store that would map pointers to values, and then the continuation. However, recall that I told you that you kind of don't really want to use a store in your C program because C already has mutation. You might as well leave it alone. So what is the technique that you can do? Well, there's a much more interesting way to implement our J7 language. And here's the more interesting way to do it. What we can do is we can write a translator from J7 down to J6. Now remember, J7 has variables, and J6 only has boxes, but no variables. Right? Now how does that work? The idea is that inside of your code, there's going to be a lambda x somewhere, something that establishes a variable. And then in there, there's going to be some references to x. And then there might be a set that goes to x. And then there might be some more. Okay? And what the translator is going to do is it's going to turn this into the following. It's going to turn it into lambda xi, that I is for the initializer of it. Then it's going to say let x equal box of xi in, and then it's going to find that x right there and change it into unbox x, find that set and turn it into setbox xe, and find that x and turn it into unbox x. Okay? So the idea here is that your translator is going to identify every time that you allocate a variable and then change it so that it now is boxed. Okay? So how can we really do that, and what is this translator? Well, the translator is, of course, just part of your desugarer. You just make it so that your desugar has the following rule. When you call desugar and you get a lambda with a recursive name, which I'll write as, actually let's write it as f, a recursive name f, and then I'm going to do it for just one variable, but you can make it for multiple. One variable, and then a body. Okay. Then what we're going to do is we're going to turn this into calling desugar on lambda. Sorry, not calling desugar. We're going to create an actual lambda that has f and then xi. And then inside, we're going to call desugar on a let of x, of x equal to xi in, now b right here. How are we going to do b? Well, what we're going to do there is we're going to add to the desugarer an extra argument, which is the boxed variables. The boxed variables. And so we're going to call the desugar, this just has this normal BV. We're going to call the desugarer here on BV prime and B. Now what's BV prime? BV prime is just B, V, with one more thing, which is a mapping, with that just says X. Okay? Then your desugarer is going to also have a case for a variable like X. So it's going to have the box variables in X. And then it's going to say, if X is in the box variables, then we're going to return unbox of X. Otherwise, we're just going to return X. Okay? And you, of course, start off your box variables as empty. Now, if we want, we can make this even smarter. And here's how we can make it smarter. What we could do is we could say, if modified B, then do this. Otherwise, do a normal lambda. Now, what do I mean by modified? Modified would be a function that would look through this B and see if it ever actually did do a set. That way, if it actually did a set, then it could box it, and otherwise it wouldn't. Because, of course, it's expensive to do a box because you have to actually store the thing in a box somewhere. Okay, so this is a way that we can take our language that has mutation and add support for variables without actually changing the underlying language. Now there's one last thing that we really want to add to our desugarer at this point, which is that we want to add mutually recursive functions. Way back when we had, I believe, J2, we could write mutually recursive functions like this. We could write a function like even question mark that says if x is equal to 0, then return true. Otherwise, return not odd of x minus 1. And then we could define odd as if x equals 0, false. Otherwise, do not of even x minus 1. So this is a classic pair of mutually recursive functions. When we added recursion earlier in the language, we didn't actually make it so it was possible to do something like this, because only one function could be recursive, not multiple of them. So how can we deal with that? Well, we implement it inside of the desugarer. What we do is we take a form that's called letrec, and letrec is going to have a sequence of variables, and each one of those variables is going to be bound in a context where they can all see each other. All right? And here's the way that it works. Oh yeah, and then there's a body. Okay, so we're going to turn that into the following. We're going to turn it into a let, where we define each one of the variables as unit. Then once we define them all as unit, then what we do is we set each one to the corresponding expression. And then we have the body. Now what that does is it makes it so that these expressions right here, each one of them is bound inside of a context that has access to all of the variables. Okay, so let rec is a very common desugaring step. This is something that you put in your desugarer. So it's a very common desugaring step. And now we have mutual recursion in our language. All right, I think that is all for today. I feel like I went a little bit fast there, but that's okay. Next time we'll have more to say about the next language feature.